Scenario: a tether ball of mass m swings in a horizontal circle at the end of a rope of radius r at an initial tangential speed v0. As it undergoes uniform centripetal motion, the rope starts to wrap around the pole such that the radius of the circle decreases. Question: the prediction by describing the angular momentum of the ball when the radius decreases. Let's take a look. The angular momentum of the ball will actually remain constant because there is no net torque exerted on the ball to increase or decrease the momentum of the ball. So the equation of the momentum of the ball of L remains L because the I is the same and the angular velocity is the same. There was no net torque to increase the angular velocity in any way. Therefore, the angular momentum of the ball remains constant, even though the radius decreases. The next question: what are your predictions by describing the rotational inertia of the ball about the axle of rotation? Well, the rotational inertia is proportional to mr squared. That is the I value. The I value is technically equal to mr squared. Sometimes there's a constant in front. Okay. Notice that there is a radius in the calculation for rotational inertia. When the radius decreases, the rotational inertia of the ball will decrease as well. I wrote the equation. When I goes down, the R will also go down as a result. So here the rotational inertia will actually decrease as a result of the radius decreasing. This leads us to our last question. I want your prediction by describing the final angular velocity of the ball. Well, the final angular velocity is actually greater than the initial angular velocity. Why? Since angular momentum is conserved and the rotation inertia decreases, that L is equal to L naught. That's the conservation of angular momentum. And I broke it up into its equation. So rotation inertia times angular velocity final is equal to its initial. Notice that I is going to go down because radius go down. That was the last question. As a result, the angular velocity actually has to increase. That is because that's going to be equal to a constant value due to conservation of angular momentum. Okay, so the angular velocity of the tetherball will actually increase. That's why if you remember playing the game of tetherball, as you hit the ball and it swings up the rope, as it gets closer and closer to the pole, it starts speeding up. That is because of this property. Rotational inertia goes down, the angular velocity goes up.